All right, last lesson for Unit 6, so a short one. So electrolytic cells. So far we've talked about spontaneous voltaic cells. Now we're going to talk about these non-spontaneous electrolytic cells. All right, so by the end of this, you'll be able to decide if something is going to be spontaneous or not, and describe differences between electrolytic cells and voltaic cells. So electrolytic cells look very similar to your voltaic cells, especially your wet voltaic cells. There's going to be an anode and a cathode. The anode is going to have oxidation, the cathode is going to have reduction. All right? But the biggest noticeable difference is that an electrolytic cell is going to require some sort of outside energy source, such as a battery or a plug, so that it's connected to electricity. All right, and that is because they are non-spontaneous. We have to provide some energy to force this reaction to go against spontaneity. So, just like the voltaic cell, the anode has oxidation, and the cathode has reduction. All right, that is the same. That's true for all electrochemical cells. Anode is always where oxidation occurs. Reduction is always where, or the cathode is always where reduction occurs, okay? So which of these reactions belongs at the anode? All right. So anode is oxidation. Which of these reactions shows oxidation? All right, oxidation is LEO, losing electrons. So this reaction is happening here. And then, if you're using a metal, the same metal for both the anode and the cathode, that's not going to happen spontaneously. So this is a way you can force like electroplating. All right, so our cathode will have the reduction, or where we combine the electron and the ion to make gold. So we could plate gold on those frames. All right, so this is where this reactivity series comes in again. All right, so these ones up here, most active, are going to naturally, spontaneously oxidize. And these down here are going to naturally, spontaneously reduce. Using an electrolytic cell, we can reverse this. All right, we can force these guys to oxidize. And we can force the other ones to reduce, so that we can, maybe plate with some silver, or plate with some gold or copper. So, of the metals, lead, mercury, sodium, and calcium, which would be the most difficult to oxidize? Lead, mercury, sodium, or calcium? There's calcium. There's sodium. There's lead. And there's mercury. All right, so mercury would be your hardest one to oxidize. So that one is probably going to require an electrolytic cell for us to get that to happen. So which of the following would most likely be an electrolytic cell? All right, so let's look at this. We've got aluminum coating on iron. So aluminum, iron. And then iron onto lead. And we can also, we're comparing copper and tin. So this one's going that way. Then calcium onto iron. So we have 3 going in the downward direction and 1 going upwards. All right, so coding something active onto something not active is fairly easy to do. Coding something not active onto something that is active is hard. So it's this yellow one, the copper on a tin, that's going to require your electrolytic cell. All right, the most known or discussed use of electrolytic cells is usually electroplating, which means that you're going to coat a thin layer of a different kind of metal on the outside of something. This is done a lot with gold. Gold is one of the least active metals, so this is often used to, jewelry or things like that might just be a thin gold layer and then a cheaper, less expensive metal underneath. Another example of electrolytic cells is electrolysis, and you can use this to split compounds into their pure elements. All right, so for example, you can take sodium chloride and split it into chlorine gas and sodium ions using an electrolytic cell.